All right, I think most people have joined by now. So let's give a start to the October series of the RIOT Science Club. Today we are here with Dr. Marion Criaud, and I want to thank you all for coming and thank her for giving a talk. Just a few things before we start. So you can find in our Q&A more information about the RIOT Science Club, which is an initiative that wants to bring more awareness towards a reproducible, interpretable, open and transparent science. And in the Q&A, you can also post each and every one of your questions. Please feel free to post from the beginning of the talk and throughout the talk. Marion is very much happy to take your questions throughout, and she will want these to be as interactive as possible. Now, talking about Marion's experience, she is currently a postdoctoral researcher at King's College London, where she studies fMRI and NeuroFeedback, which is a new treatment for children with ADHD. And we are especially excited to have her here today because she is also part of the RIOT Science Club, where at KCL she is a fantastic organizer and a great proponent for the best practices in fMRI. So that's also what she's going to talk today about. So the pitfalls of fMRI analysis and how we can address these. So Marion, I'll actually leave the floor to you now. Thank you for joining us again.
Hi, everyone. Thank you for having me. I'm very, really happy to be here and representing the riots in Rotterdam. That's exciting. So just a tiny bit about myself before I start. So I've been working in neuroimage for a long time now. It's been about 11 years, mainly with fMRI, a tiny bit of PET as well. But I've been working with task-based fMRI, resting state, and now neurofeedback. And like anybody else, I had to learn the hard way what to do, what not to do. And that's what we're going to talk about today. So the pitfalls of fMRI analysis. Well, we all know fMRI and how sensible it is. So let's see what we can do to make it a tiny bit more reproducible. So we know there are problems of reproducibility in fMRI. To find ways to, find the same results, if it's your own study, if it's someone else's study, if it's the same design that you change a tiny bit, everything can go very, very wrong. And that's the case in psychology, but in fMRI, even worse. Anything can have an impact on your data, anything. And so here's a list of few things that I came across in my 11 years of experience. And so you can see some of these are just, basic things. Water consumption. Are you going to ask your participants to have the same amount of water before they come into your experiment? That's silly, really, but it does have an impact. Obviously, drug and substance abuse, caffeine, all of this, and attention, fatigue. All of these have influence on your data. But what we do with fMRI also has a massive impact on the data. We have all these parameters that, are completely different from one experiment to the other. The scanner you use, the version of the scanner you use, the brand of the scanner, and you know how many brands there are. I was actually surprised when I did the research. It's unbelievable. The way you acquire the data, how you say the instructions to the participant, how you process the data, how you analyze it, the task you give to the participants, and the participants themselves. So yes, I work with ADHD kids, and as you can understand, this is a challenge. Obviously, this is the part where participants and performances are really affected and will affect, the data themselves. Ask a kid to be for an hour lying down in an fMRI machine without moving. That's a challenge. We'll see later on. Hopefully, I'll be able to show you exactly how much of a challenge this is. So obviously, we start with the acquisition parameters. So like I said, machine brand, power, type of acquisition, and the sequences you use, all of these will have an impact on the data because this is the data, really. So if you want to make fMRI reproducible, you will not be able to say, I don't want to use that GE machine, I want to use that Siemens. No, you'll use what you have, obviously, what is in your center. But you need to make do, and you need to be able to report all of this very thoroughly to make sure that another person will be able to reproduce your data. But bear in mind that this has an impact on the reproducibility of fMRI. For example, sequences. I'm not sure a lot of people are aware of the spiral sequence, but here you have two kinds of sequences. The EPI is the most used here in the UK, and spiral, which I came across when I went to work in Toronto for a bit. It's basically the way the case space is divided, or it's acquired. The data is acquired in the case space, sorry. It's just two different ways to do it, and it's supposed to be quite equivalent, but it's not quite. So you need to be a tiny bit aware of this. So for example, if you look at this paper from Gary Glover in 2012, you can see that on the top, it shows the massive artifacts that are apparent in EPI data. This is just the way the data is acquired. This is just the way the sequence is working. So you will have artifacts near to the cavities. So, all the ear and sinuses, this will create problems in your data. Gary, when he created the spiral in and out sequences, got rid of these artifacts. Problem is, there were other artifacts specifically related to the spiral sequence. I don't know if you can see it properly here, but you can see some kind of zebra kind of things here and there. And this is very, very specific to spiral. Other artifacts came across later on, but basically, no matter what you do, no matter what sequence you use, you will get specific artifacts. So keep that in mind, because for EPA especially, these artifacts can be quite big, but they are manageable. There are ways you can counter them, and that's when you use the field map acquisition. But you need to know about this in advance. So no matter what you do, you will not have a choice, but you can get ahead of this by learning about the sequences you're using or the machine you're using. Now, obviously, all these acquisition parameters, they go along with your protocol and everything you do with fMRI. So that's very advanced. I'm not going to go into details about this. Just know that if you have an fMRI experiment, or if you're designing an fMRI experiment, you will have to know all of these parameters, and you will have to be able to kind of either justify them or use them properly later on. Keep that in mind. We'll talk later about the repetition time and the slices, the acquisition order, but we won't go into all the details about everything that is going on here. It's a tiny bit advanced for us right now. Repetition time, so like I said, we are going to talk about it a tiny bit because we need to. Just for people who don't necessarily know, in fMRI you acquire volumes. So this, or my head, would be a volume. That's a 3D image full of voxels, and that represents the signal that is in your brain at one point in time. Now, we don't acquire this volume instantly. We acquire it by slices, right? So all of these things that you see here are slices. And put together, assembled, they are a volume. Right. The problem is, to acquire all of these slices, it takes about 2 seconds, or it takes about the repetition time that you need. So there is a time difference between the first slice that is acquired and the last slice that is acquired. That is important, and we need to keep that in mind. If you want to have very, very precise fMRI acquisition in terms of time, you can shorten your repetition time, but it means you will also shorten the space you're acquiring. So you can have, for example, for motor acquisitions, I know they are targeting sometimes between the SMA, pre-SMA, motor cortex, and this is a very, very tiny band, and this way you can have very, very fast repetition time because you don't need a lot of slices in the end. But if you want to have a whole brain, a whole volume, then you will need to have around 2 seconds of repetition time. That is about it. So all of these and the choice you make for your repetition time, it has to be thought through. Why do you need this? Do you need the entire brain? Do you need the cerebellum? Do you need the top of the brain? Do you need big slices? Do you need gaps in between? Why do you need all of these? If you're targeting one specific thing and you can erase the rest and you're sure that you're never, ever, ever going to need the rest, then fair. You can only have half of the brain if you want to. You just have to justify yourself. Right. Now, data processing is going to be the main part of the talk, so I'm not going to go into that just yet. But data analysis will have impact on the data as well. And when I say data analysis, I'm talking about stats. So stats need to be thought through ahead of time. Before you think about anything, what is it you're doing? Why do you do a block design instead of an event related? What exactly are you going to do? What model are you going to use to do your stats at the end? If you don't think this through before, you might end up with data that you will not be able to analyze properly at the end. So think this through very thoroughly before you start. What kind of model, what kind of event are you going to be able to model the timing of the events? Are you going to derive the HRF in a certain way just to compensate for something in your protocol? Think this through, because this has an impact on your data as well and how you're going to get your protocol ready. Now, correcting for multiple comparison, I'm just making a tiny bit of a point here. It's extremely hard to get very good data, very good quality that are significant at the end, with significant results, at the end, that pass corrected threshold for multiple comparison. Basically, when you correct for multiple comparison in fMRI, you correct for the number of voxels in the brain. We have a lot of voxels in the brains when we acquire them, so we make a lot of corrections. And a lot of people think that, it's very hard to pass this barrier of correction, so you might just publish with uncorrected results. And sometimes it's fine, but most of the time, you should go towards corrected analysis. And this paper is a very good example of what can go wrong when you don't correct for multiple comparison and when you just are a bit lenient with your threshold. These lovely people found brain activation in the brain of a dead salmon. Yeah, the fish. That went and, had apparently some thoughts that went through his mind. Can you still hear me?
Yes, Marion, I can.
Okay. Brilliant. I thought I had a problem of connection for a second. Cool. So then we also have a very big publication bias when it comes to fMRI. I won't go into it, but basically trying to publish non-significant results is extremely hard sometimes. At least it was in the past, because that was my first results of my first fMRI analysis. Was not significant where it was supposed to be. And, that's not easy to publish. I was able to publish this paper in 2017, and I did this experiment in 2012. So it gives you an idea of how bad this was and how hard it was to just publish it. Obviously, everything else related to, an fMRI task is going to have an impact on your data. So I'm just going to move quickly to the task, the design that you get, and then obviously the participants' compliance or the disorder like ADHD or age of the participants. All of this will have an impact. Now the fun bit. So I love this bit. It's my work. It's my babies. All of the data processing, I just love it so much. And I'm very, very happy to share my data with you and all of the problems that I had in the past. So everything that I show you are actual data that I had and all the problems that I encountered. Be gentle, all of this was corrected before publication. But it was a surprise sometimes. This is when, if you have any questions about fMRI and how to process data, or if you have specific problems with your data, please feel free to ask questions in the Q&A, and I'll be happy to answer them. So, processing data, pre-processing especially. All of this is to clean the data, because fMRI data is super noisy. It's very sensitive. You have artifacts all over the place. You have signal outside the brain, you have the brain, you have the CSF, you have the skull, you have the fat, you have all of it. Let's try to clean the data, make sure that everything we have is neat. Fine, fair. But when you do this, you are manipulating the data. And that has a very strong impact. It could be a very good impact, but it could be a very bad impact as well. So let's see what we can do. The idea is we do need to manipulate the data at least a tiny bit. If I tell you that I work with ADHD and they move a lot, you need to correct for movements, and you need to correct a lot for kids with ADHD, obviously. So basically, you want to make sure that all of this is removed, and you want to reduce the source of false positive errors. But you want to make sure that you're not increasing also, negative errors or, weird things that can happen in fMRI. So let's go into details. Oh yeah, one thing that is a bit surprising is we've been working with fMRI since about 1992, and yet we don't have any consensus about how to process the data. So it's a bit troubling. We're working on it. The community, everybody's working on it, trying to find proper pipelines, but there's no consensus just yet. Let me just, there's a question. That's a very good question that is being asked in the Q&A, and I'm just going to take a second to respond. Open data and violating confidentiality, that's a very, very good question. So yes, we want to go forward with fMRI and be able to give our data in platforms like OSF or other kind of servers where you will be able to find the data. It creates a few problems. The first one is obviously confidentiality. With fMRI comes usually an MRI image, which is a high-resolution image. And with this, you should be able to reconstruct a 3D brain and a 3D face, which means you can technically identify the person that was in the MRI machine. Not necessarily great, I agree. But then you also have a problem of how do you give the raw data to the platform like OSF? The data that is given to us from the radiographers to us is already manipulated. It's being reconstructed in a way, and sometimes some other manipulations have been done on it, so we don't have much power over it. It's very hard to know exactly what to do with fMRI. Some people say that to counter the confidentiality side, we should all do skull stripping, so erase everything that is related to the skull, fat, anything, so we cannot reconstruct the face. That could help, but then you're already manipulating the data. Now, because the data is already manipulated in some way, if you disclose exactly what manipulation, how the data was given to you, and what you did to make sure that people keep their data confidential, then it might make it okay. It's an ongoing problem. There's not real solutions. I think Raspoldrack is working on something like this, and I know some data is available with Human Brain Connectome and projects like that. But if you need to give your data to someone, or if you need, like, say, a journal asks you for the data that you've been working on, you need to think this through, and you need to be able to report everything very, very thoroughly. I'd say for the confidentiality problem, skull strip, that would be the main thing. But for every manipulation you do, you have to report it. So if you did skull stripping, say exactly what you've done. If you use different threshold for each participant, tell exactly what you've done as well, so that people can understand where the data come from and what they are exactly. But yeah, this is a very good question. So, pipelines and debates, yes. So there are a lot of pipelines and a lot of debates about what we can do about fMRI data when we preprocess the data. Some people say that some software are better than others. Some say that some pipelines are better than others. Some people have spent their entire career trying to figure out what pipeline works best. And we still don't have one answer. So fMRI prep is good in a way. They're trying to find this solution, the solution to the pipeline problem. And I'm going to use it just to give you an example of how you can see the process data, the process pipelines. But I have some reservations on fMRI prep. So it's good, but you have to study it and be careful with what you do with it. I won't go into too much details, but just be mindful that you need to understand exactly what it's doing to your data before you use it. And I think that's not quite straightforward. But anyway, so if you have your data, you have different ways to analyze it. And this summarizes some of the ways you can analyze it and what order you should use to analyze your data. So head motion, slice timing, and then you have all the distortions if it's needed, and then you realign the data. The order of preprocessing will come with your design, based on event-related or block design, or if you want to do functional connectivity or not. All of this will change your pipeline and the order of the preprocessing. This is just a good example of a lot of things that you need to do to your data, and you can understand that if one tiny thing goes wrong in one tiny place, then everything goes wrong. So just be mindful of that. If you want to use fMRI prep, it's very good. Read a lot about it. If you want to use other pipeline, create your own. I think it's the best way to go. But just think this through ahead of time. I'm not going to go too much into this, but we're going to start by data checking. So that's the main thing I want to talk about today. And I will repeat this over and over and over again. Whatever you do, you check your data. You check it when it's given to you. You need to make sure that it was given to you properly, that the image is not cropped, that you have the entire brain. If you don't have the entire brain, what happened? Was it during acquisition, during reconstruction? Could you ask for the data? Check your data. So you check it when it's completely raw, and then you check it every step of the way. I insist on that because people think, yeah, I have the data, it's all fine. And then they end up with activation only, at the bottom of the brain, because they didn't realize that one participant didn't have the full acquisition, and everything is messed up. So if you think about it, it takes a lot of time, and you check all the data, but then you're confident with everything else you do. So it's just a peace of mind, and it's actually a lot more efficient to do it this way. So I'll read some comments in a bit. I'll just show you first what data checking can look like. So these are 3 of my participants that I worked with in my career. These are not fMRI data. These are structural data. When you acquire fMRI, usually you have one high-resolution image, and this is one of them. So on the left, we have one young-age participant, student, about 20. Nothing goes wrong, really. And in the middle, you have a nice kid with ADHD. So this is acquired in about 5 minutes, and it's supposed to be very high resolution. You're supposed to be able to see, gray and white matter, the ventricles, even, some structures. You're able to delineate all of this. In this one, you're not. Let's face it, this one is just so blurry, there's nothing you can do about it. And on the far right, you have one of my patients with Parkinson's disease. Lovely person, but obviously you see there are differences between this one and this one. Parkinson's being a neurodegeneration disease, well, you will have ventricles that are a bit larger than anywhere else. You will have sulci that are a bit bigger as well. Keep that in mind. You need to know these things before you process your data. You might think that something is wrong with your fMRI data when actually it's just the ventricles that are a tiny bit bigger. So just keep all that in mind when you check your data and check everything from structural to functional. I'm just going to read Sam's comment. Just give me a second. Yes, that's true. I didn't really talk about consent, but consent to give the data is now something that we need to think about when we organize a protocol. Although a lot of consent forms now say that they allow the data to be published. And depending how you read it, that comes into play as well about publishing the raw data as well. So I'm going to move on to slice timing. This is what I usually do first in my data analysis. So like we said earlier, we have all these slices that form a volume. And because they have a time difference between the first and the last slice, you might want to homogenize everything with the slice timing. Slice timing is basically just making sure that you don't have a gap of 2 seconds between the first and the last slice. That's all it is. Now, you need to know all your parameters. So what order do you acquire the data? Is it interleaved or is it sequential? So sequential is just from top to bottom or bottom to top, just one at a time. Interleaved would be all the odd first and then the evens in one way or the other. You need to know if it's top to bottom, bottom to top, whatever way. And you need to obviously know your repetition time. If your repetition time is above 3 seconds, there is no point in doing a slice timing. It will just induce noise. Now, if your TR is about 2 seconds, one can wonder, how does it work exactly when you do slice timing? You are making a temporal interpolation, some kind of a smoothing based on, the middle slice that you have. Is it good for your data to do that? Is it needed? Are you sure that the interpolation that will be done is relevant and important? Do you really want to impose that noise? There have been a debate for the last 10 years about this, and now software are tending to move away from slice timing, and they found a new way to deal with this. FSL has a very elegant way to deal with this at the GLM level, so at the first level analysis. Now, my advice is, whether you do or you don't do it, justify yourself. If you want to do some very fancy analysis and you designed your entire protocol for a DCM analysis, then you won't have to do slice timing. DCM has its own slice timing interpolation, so you don't need to do it. More likely, you should not do it. So just bear that in mind. If you want to do some kind of connectivity seed-based analysis, or if you want to do some simple things, maybe you want to consider it. But you need to be able to justify yourself. Why did you do it, or why are you not doing it? What do you think fits? Do you think it's going to add more noise? Think about this. And check your data after it's done. Motion correction, and that's where the fun starts. So, here on the right, we have one volume of one of my participants, current participants, kid with ADHD. And here at the bottom, you have the movement parameters. So when you do fMRI, eventually you will get 3 movement parameters that are in all three axes, so X, Y, Z, and then all the rotation around it. So 6 movement parameters in total. If you use FSL, it will display for each movement parameter exactly the amount of movement you can see. And for this one, doesn't seem like there is much. We are talking here in millimeters, and you never want to go higher than the size of your voxel. So if your voxel is 3 millimeter, you want to stay in that range. Now, this one seems to be fine in terms of, in terms of millimeters, but you see here we have such a massive movement that some slices seem to go out of the brain. And well, that's almost uncorrectable. Unfortunately, there's not much we can do about this. So we will still try to correct the data. We will still go through with the analysis, but what I advise you to do is have a massive spreadsheet, put all the participants and all the processes, and write down for this specific participant, terrible movement, keep an eye on this participant. You'll see at the end whether it's corrected or not. Another of our lovely participant started the acquisition with a brain facing like this, and then for some reason something happened. I don't know. They sneezed, or they decided they were not comfortable, whatever happened, and they had about, let's say, 12, 13 millimeter movement in the middle, and that gives a repositioning that looks like this. This is hard to correct as well. there's not much we can do. I mean, we can try again our best, put a mark on it and say, red flag here as well, very big movements, but you'll have to wait and see. One way to see it, if your motion correction was working, is to look at your data at the end. So this is statistical map, first level analysis. If you see that you have activation in the ventricle, well, something went wrong. Ventricles, well, they don't really activate, right? No matter what you ask the participant to do, there's not much there. So you should never, ever see activation in the ventricles. White matter, I would say it depends. Here, this one is clearly, in the white matter, this one is borderline. Check if you're in a specific structure or borderline before you exclude the participant or the cluster. But when it's clearly in the ventricle, there's nothing there, really. Another way to find out if your motion correction worked was with what we call ring artifact. So it's activation around the brain, and that goes in every kind of axe you want. It's usually bad news. When you see this is very, very specific. This means that the correction was not, the motion correction did not work properly. And obviously when you did your analysis, it found differences in these edging areas, and this is what comes up. So obviously you have a very good activation here and there, but then because of this, you might wonder, actually, is this activation or is this also borderline movement related? And that gets complicated. So if I was in that situation and I saw that, I would go back to motion correction for this participant, try to find maybe a most robust way to deal with this, because you don't want to publish that. That's not good. And you don't want to bring that to the group level analysis either, because you don't know how this is going to work, how this is going to impact the group analysis. Now, before I go into the details of what different movement types and stuff, I'm going to try and share with you my current work and see what you can do to check movements. So let me unshare this screen and share the other one. Right, so you should be able to see some brain already.
Yes, it works.
Perfect. So this is FSL View. FSL View is one of the best tools I use to check the data. Right now it's on movie mode, so you can see the number of volume here is going from 0 to 224. So it's basically the movie of your time series. And this kid, for some reason, was being very good, barely moved in the machine, and you can barely see anything wrong. So that's brilliant. That's what you want to see. Now, let's check another one, just for fun. This one is another one of my participants. So this is when it's not moving, and let's see the movie mode here. And we go on an adventure. Here we are, all over the place. Whoa! So I'm just going to slow down a tiny bit to show you exactly what happens. But this kid moved so much that eventually the brain kind of splits. So we are acquiring data into leaves at that point, and obviously you can see the slices being acquired at 2 different times. But this kid moved so much within the 2 seconds that we have a potato brain kind of sliced at the edge. This is not good. This is something that is, you go from positions to positions. It's ridiculous. Plus this kind of split thing. There's nothing we can do about this. So when I said check your data, this was spotted with the raw data, obviously. And then we checked the movement parameters for this kid. All of this was written down, and we tried to do motion correction. I need to say, I'm not sure it worked. I don't have the sheet right now to tell you if it did, but I doubt it did for this kid. But these are things that you need to write down. So if we see this from the raw data, we are not surprised at the end when we see that there are still problems, right? So these are just 2 examples of what can happen with movement and how to check these movements. So I'm going to share again my slides. Yes. All right, so just to finish quickly on the motion parameters, different kind of motions. You have the big ones that happen, they sneeze, they move a tiny bit, fine. You have the very big movements. So these are movements from my patients with Parkinson's disease, a lot of tremor. And then you have drifts. Of all these movements, drifts are the harder to correct because motion correction goes from one volume to the other and it calculates the movement between one and the other and then corrects for it. A drift is a movement that is very small from one volume to the other, but from end to end is massive. So it's really hard to detect for the software and then to correct. Just keep that in mind. Again, the way you do your motion correction, you will have to think about how you want to do it, what volume of reference, what session of reference, if you have different sessions, if you want to do all your runs at once or one per one or run per run. And motion regression is something that we all do at the first level analysis, where you put your motion parameters in your first level analysis. Now, that's classic. You can put 6 movement parameters per participant, but now Tristan just said that maybe 24 is good. And based on some of the data that we are currently having and processing, the 24 parameters are quite good in the first level analysis. So just think about how you want to correct your data. Depending on who you work with, if you work with students who are 22 and when you tell them to be in the machine and they stay very still, you might not need to use the 24 movement parameters. But if you have kids with ADHD or patients with Parkinson's disease, you will definitely have to. So, co-registration. So just trying to align 2 different modalities, basically. So working on your functional data and making sure that it matches the space of your high-resolution image. It's important just because we want to make sure that, let's say you are working on the frontal region of your functional image, you want to be able to relate it to the frontal region of the MRI image. That is important, and that's also needed for the normalization later. And you think that it's straightforward, but it's not. This is what happened to some of my participants, so I'll explain a tiny bit. But in red here, you have the overline of what it's supposed to be. And here in gray behind it, you have the actual functional image. And if you think about this, it's completely flipped and looking down. So this is the frontal region, this is the cerebellum, and this is cut here because it's the end of the image. And that happened a couple of times with a couple of participants because I went from one software to another. Something I don't have time to talk about today, but when you want to work with fMRI, you will have to choose one software. The most famous ones are AFNI, FSL, and SPM. And you'd think that by now they can all work together. They don't. If you want to work from FSL to SPM, it's extremely hard. SPM has a really hard time to read FSL data, but it also works the other way around. If you start with SPM to FSL, you will have a hard time. Less of a hard time, but still. Keep that in mind. One thing to also keep in mind very quickly, when software update, it might change your analysis. So have somewhere written, what software version you're using and keep it consistent. Don't do any updates while you're doing your analysis. Just keep that in mind. Segmentation. So here it's for fancy analysis where you want to work on your high resolution image, structural image. Sometimes you want to do a segmentation to be able to extract the gray and white matter, and you want to get rid of everything else. So here is the image of origin, and here is the gray matter, and here is the white matter, and that's when it's working. That's perfect, that's brilliant. And that's when it's not working. I don't have to tell you why it's not working here. I mean, clearly we have like one blob and nothing. Here the delimitation is just a bit random. And same here. So again, all of this means one thing. Just check your data. I'll go on and on about this, but this can happen, and that happens more often than you'd think. The software decided that it was not going to work that day. Maybe the server went down. Maybe something that the data is a tiny bit more complicated to process because you're working with kids who have a smaller head and the software doesn't read the data properly. Who knows? It can happen, but it doesn't matter as long as you know it happened and you can go back and work on it. If you don't even know that it happens, then you might end up with very complicated data at the end, and the stats might not mean anything because you're working with things that are not what you want to work with. So just, again, check your data. Normalisation. So that's when we are taking all the data from all the participants and try to match it to a template. This is very useful because at the end, when you publish your paper and you say we have activation in the DLPFC, you want to make sure you're in the DLPFC, not just for your participants, but for the general population. One thing I'd say first, and that's my own bias, but some people match it to the Telerak template, some people match it to the MRI. May I say, the Telerak is extremely old, and it was done on half a brain of a very old lady. It was useful a long time ago, but it's not anymore. So if we could all move on to something else, that would be lovely. I personally like the MRI. Choose your own template, but can we forget about the Telerak? That would be a very big step forward for the MRI community. So that's my own personal message, but do what as you will, as long as you can justify yourself at the end again. So normalisation, again, we go from a brain that looks like this, and amazingly, after normalisation and a tiny bit of smoothing, you end up with this. It's a round brain, it looks amazing, and it feels like everything went well, except for this participant. That got stretched a tiny bit, and it does not look round at all. It looks like a potato. Again, this happened to one of my participants eventually, so I had to go back into it. And normalisation, for some reason, is one of the things that can be messed up very easily, very, very easily. So don't be afraid if it happens, just keep it in mind and correct it. You'll have ways to correct it. You might have to change a tiny bit of parameters for the specific participant, or just sometimes just rerun it. Again, I work mainly on FSL. I love FSL. I code it with it very easily. A lot of people work with SPM, and it's fine. SPM is a straightforward tool, but SPM and MATLAB are very temperamental. And sometimes when you click on a button, it works. And sometimes you click on the same button, you do the same thing, it doesn't. So when something happens like this, and you're working with SPM, the first thing you need to do is redo the same analysis exactly the same way you've done before, because sometimes it's just a matter of the software not working properly. Don't try to change everything just yet. Try it a second time, especially with SPM. Don't lose hope. SPM is a bit mean sometimes. It feels like it's mean. Just keep trying. Eventually it's going to work. We've had a few examples this year with one of my students where, we did the processing 5 times for one participant, and eventually it worked. I won't be able to tell you why the 5th time it worked. Sometimes it's just the way it is. That doesn't happen as often with FSL, I have to say. But again, that's one of my preferences. So finally, everything that I tell you are things that happen to me, are things that are my preferences, are things that I've encountered. But you will have your own protocol, you will have your own design, you will have your own participants, so you will have to construct your own pipeline. You can follow something that is already done and set for you with fMRI prep, but I would advise you to think about what they do and what you need. Do as you please, do what feels also comfortable. Sometimes people will try to force you to use softwares that you don't necessarily work well with. Just do your best, but remember that if you check your data all the way, and if you really think this through, if you really have good reasons to do everything that you do, when you report it, and if you report it very thoroughly, you would have done the best that you can, and that's the aim at the end. fMRI is unfortunately highly unstable, and sometimes you might lose participants because they're unprocessable, like this participant I showed you, where the brain can split. That's unfortunate, but that's the way it is. But one thing I would also say is talk amongst yourself. That's something that I learned later in my career, but we all have the same problems when it comes to fMRI. We all encounter some things that are similar. So if you want to go and have a chat with the person next door who's doing something a tiny bit different but with the same modality, go and talk to them and say, hey, I'm stuck with this. They might have been stuck on the same thing for 6 months before and found a solution already. Who knows? I do love fMRI, and I do love all of these. I do love processing the data. That's really why I'm doing what I'm doing now. I know how frustrating it can be, but just keep with it. It's an amazing tool at the end of the day. The last thing I want to say is, I don't have time to go into details, but if you want to make fMRI reproducible, you need to be able to report everything you do. And when I say everything you do, it means everything I talked about today, step by step, everything. So what was the brand of your machine? What was the sequence you used? How many slices? What was the TR, the TE, all of it? What was the software you used, the version of the software you used? If you use SPM12, what version of MATLAB you're using? What OS were you working on? Linux, MATLAB, Windows? You need to report all of this. One, it will help you to keep consistency. And two, it will make it a lot easier for people to understand why they're not running exactly the same thing. It's a lot easier for me to understand that we're not using the same version of MATLAB, so I can go back to the version you used and try to find something similar instead of just, publishing something and saying you were wrong. So try to report as much as you can. And if you had issues with some participants and you had to apply some specific pipelines for them, some more robust movement corrections, some specific things, because sometimes it happens, write it down. Just show examples in your paper, have supplements, don't hesitate. That's the only way we can actually move forward. So there are other things we don't control with fMRI, but there are things we do control. Is how we design the pipelines we use and how we justify it and we report it. So my idea would be then to, one day, I hope, we can have these kind of things where pipelines would be designed based on our specific needs. And if someone wants to work on it with me, maybe one day, just give me a shout. But I would like to be able to show someone or something what kind of data we're working on, and then the pipeline would be kind of logical for them, something that would be pre-written. Not fMRI prep is not flexible enough to do this at the moment, but maybe something that taken from fMRI prep would be more flexible and would lead to something that is logical, makes sense to everybody, and that can include your own choices of processing would be the future. But in the meantime, we can work with what we have and do the best we can. And hopefully that will help. Thank you.
Thank you, Marion. That was great. I hear some echo.
Oh, it's probably me. Sorry.
All right. Let's give this a try. We've got a few questions. Actually, first of all, thanks for the talk. I really enjoyed it. I found it really useful also for myself. Also quite funny. It was nice to see, to hear about the potato brains as well. While talking about these issues in fMRI.
Potato brains happen more often than you think, really.
Yeah, I can imagine. So I actually see a message from Olivia with a checklist for reporting fMRI. Yes. Thanks, Olivia.
The COBE does that guideline. They're quite thorough of what you need to report. So if you don't know what to report, that's true. The COBE does guideline are there for you. Tick the boxes when you say that's reported, and then it makes it a lot easier. That's true. Thanks, Olivia.
And then moving on, we have another question on whether you have any reading list to ease people into fMRI or how to make fMRI reproducible.
That's a very tough question, to be honest. I have to be honest with you. I don't have a reading list to ease people into fMRI. What I would suggest to you is if you have the tiny bit of money to go into a conference or to go into a course, FSL and SPM courses are quite good. I would go towards the FSL course because it's a lot easier to understand. It's sort of more friendly. But the SPM courses are also amazing. SPM has courses in Zurich and London usually. FSL courses are also available on the websites. I say that, and I understand that it's all about analysis already, but it gives you background on what the data is and what the signal is. And it eases you into this. So I think these would be my first go. FSL especially because it's online already. You have the PowerPoint, you have everything there. So that would be my first thing. As for fMRI and reproducibility, I would say follow Russell Poldrack. He's the biggest guy working on reproducibility in fMRI. Matt Wall is also a big name. We had a couple of talks in the last year of RIOT and KCL that we can have access to that will give you clues towards this. These guys are some of the best. So fMRI Prep was developed with Russell Poldrack. So he knows all about it and about open data as well. He's trying to work on a few platforms to help with this. So can we put their names in the chat? I can make an announcement, actually. Sorry, I always feel like a grandma with this technology. And I use it every week, so.
I think we all feel like that at this moment.
Cool. So Russell Poldrack and Matt Wall, yes. These are big names to follow.
And I think you briefly touched upon this, but Russell Poldrack is actually developing a new method, putting together different pipelines, right?
Yes. So yeah, I think that would be the goal later to put that together. I mean, fMRI Prep is still kind of in development, yes and no, but yeah, hopefully he will be able to put some kind of Frankenstein kind of pipeline. That's what I would like to see.
Fingers crossed.
Sam has a question about preregistration. That's a very good question, Sam. So the question is, do you recommend preregistering incrementally or a decision tree? By incrementally, I mean preregistering each stage of preprocessing and analysis, because you have to decide what to do at the next stage of preprocessing or analysis based on what you found on the previous stage. So it does make sense, Sam. So it's a very good question, and I will take an example of what happened recently with one of my students, who is Olivia, by the way. But we pre-registered a study, and we thought everything through. Because we're working with kids with ADHD, we had a very robust motion correction with art repair, and everything seemed to go well. But then when we actually started to use art repair, we realized that we were not happy with what it was doing. First of all, we were not sure what it was doing, and second, it seemed to make things a tiny bit worse than it was when we were not using it. So we decided to scrap that from our data analysis and then publish another or an amendment to our pre-registration. In that case, maybe a decision tree would be easier. But I think it doesn't necessarily need to be a decision tree, but it needs to be something that allows a tiny bit of flexibility, I agree. Something that I'm working on right now with the data analysis plan that I have for my study is we have a pipeline, but we also have, if things go wrong with, then we will do. So it's kind of a backup. It's not necessarily the entire decision tree because you can have a massive, massive one, really, but at least something with flexibility in it. I do agree. And I did pre-register to answer the question that is following. So I did pre-register. It was on as predicted, though, that being said, a tiny bit of a hiccup with this is when we actually wanted to amend our pre-registration, we had to submit a new one. They did not allow any changes in our pre-registration, which is a tiny bit of a shame because in a lot of clinical trials, when you want to change your pre-registration, it just shows this has been changed then, and that's fine. You can see why it's been changed and when. But here, we only were able to refer to the original pre-registration and then said we changed it for that reason. It didn't feel that right, to be honest. So maybe another platform would be a tiny bit easier.